was just gonna go back and get it.
Oh yeah, sure.
I was paying attention, so okay. What's the brute force method?
Brute force is like the simplest way to solve something. It's like the most straightforward way you can think about it. Like the most straightforward way you can think about a problem.
Function 5, can I see it again? The top of the function 5.
Yeah.
Oh, function 5.
Yeah, thank you. Some of my projects actually, complete. I have to work on a bit on my resume. Do you have any schedule time for that?
Yes.
Really?
Yeah, I'm pretty sure. For working on your resume and stuff? Yeah, you should be doing it throughout.
Okay, alright. That's true.
Yeah.
That's what I should do. That's what.
When's your graduation? You know?
I know, and then.
Is it July or
When is
June?
graduation done?
August. We have 9 weeks left.
August?
Yes.
Okay.
Well, thank you so much for being here.
Oh, no
Yeah, this
problem.
material's wonderful, actually, too.
Oh, no, it's all good.
Yeah, we might seem like we're like in our own world, but that's just how we comprehend it.
Oh, yeah, it's fine. You guys are fine.
It's not a very lively crowd.
No. Okay, this is gonna be fun. I'm trying to solve it over.
I get it. Okay. It looks like. No.
This is fun. This is great. You guys prefer the lights to all be on or for them all to be off? All off.
Have lights over there.
I'm sure somebody.
Was the Strange Planet? As a child.
You are.
Yeah. It's like, that would be good. Like, you want a lot.
Alright, so. Alright, so, guys. Because usually in my class, whenever I close the door, everyone just shuts up. Yeah.
We're used to playing flat.
The story goes this. Oh, I never have to do that. Yeah, I'm just close my door. That's the key word. So, I actually made a mistake when I was telling you guys this. I just realized it felt weird when I was saying it too. When you have a line, right? There's no input, right? Is that you get what I mean, right? There's no input, so that's why it's just a straight line, right? That's what I said? Oh, okay, cool. Yeah, maybe I'm just going crazy. All right, so what's the big O of this? So when this is what I mean, right? So usually when you're doing big O analysis, especially if you're writing like a complex function, right? It's probably not going to be that simple and straightforward. Okay, like it's not going to be like the cases that we did up here usually, right? That's usually not how it works, right? Usually whenever people write functions and stuff, right? It's pretty dense, right? There's a lot of code and there's a lot of stuff that's going on, right? So when you have that, when you do that, right? So you should always try to break up the code into smaller segments and try to find the big O of those smaller segments, and then do that algebraic equation thing and then simplify it, right? So that's how you end up with the result, okay? So let's break this down, right? So what is the big O of this part? Yeah, so this is O of n squared. What about this? Same thing. This is O of n, and this is, yep, O of 1, right? So what do you end up getting as a total? You get O of 2n squared, right? Plus n plus 1, right? That's what you get, right? So you actually have 2 of these n squared, so it's 2n squared. You have 1 n, and then you have 1 constant, right? So that's why you end up with 2n squared plus n plus 1, right? Which is what kind of equation is that in math? A quadratic equation, yes, right? So in big O, right? You simplify this to just what? You drop what do you drop? Yeah, so before we drop the coefficient, right? Another thing you have to keep in mind actually is in math, right? There's this thing called the degree, right? So the rightmost thing is the constant in the equation, right? Then n is has a degree of 1, right? Because it's n to the 1 power, and then it's n to the 2nd power, right? And then it will keep going, right? You could have like an n to the 3rd power, n to the 4th power and stuff, right? Which you do in calculus and shit. But what you do is when you're doing big O, you always just look at the highest degree and just scrap everything else, okay? So automatically, I'm going to scrap the n plus 1. I'm just going to have 2n squared, okay? And then we could simplify this even further by dropping the coefficient, right? So it just ends up becoming n squared. Huh? Yeah?
Yeah.
Yeah.
So patterns, the more let's say n squared repeats itself, it takes priority. The more time it repeats.
Actually, no, it has nothing to do with the amount of times it repeats. As long as there's an n squared, that's it. Okay? Yeah.
So worst case scenario? Like, when you said it takes the worst case scenario, do you mean it's for like all of the stuff inside of the function?
Mm-hmm.
Or is it like perfect for the
So technically, it's the worst case. It's the worst case for every part of the function. And then once you have the worst cases of all the little parts, you put it together and then you simplify to get the most simplified version of the worst case. Okay? So the reason for that is because, right, like, so n squared is basically that parabola, right? It's like that exponential growth, right? N is just a line, right? So it's hard to show it here, right? But let's say you were to like zoom out this graph, right? And see like a million points this way and a million points that way, right? In that grand scheme of things, right? The n and the constant doesn't matter at all. Okay, it's like it's insignificant. The thing that really matters is the thing with the highest degree, the highest power. That's the thing that matters. So that's why that ends up becoming the worst case scenario. And that's why when you simplify it, that's why that's the big O. Do you guys get what I mean by like zooming out? Like, let's say this was a graph on the computer, you would zoom out, right? Yeah. What's the big O of Func 8? But let's say you were to break this up, right? What do you get? What's the O of n for this first part? N squared. What's the O of n of this? Why say O of n cubed? Why is it O of n cubed? Yeah. The previous one. Yeah, right. So it's kind of a law, right? Like when you have loops and you start nesting loops inside loops, right? All you do is you see that what do you call that in math? The exponent, yes, right? The exponent increases. So the exponent is actually the number of nested loops, right? So the first one is 2 nested loops. That's why it's n squared. And then if you keep nesting loops, it's going to be like n cubed and n to the 4th, whatever, right? So that's basically a rule, right? You almost never ever see an n cubed or n to the 4th. If you do, you're doing something wrong. There's almost never going to be a case where you should be doing this. And even in interview questions, they will almost never ask you an n cubed. 90% of the time, all your solutions for an interview problem will probably be n to the, O of n, right? With the most efficient case, and then 10% of the time, it's probably n squared, right? So yeah. So this ends up becoming all right? But how do you simplify that? What's the rule? you keep the highest degree. Which one has the highest exponent, right? The one with the highest exponent is n cubed, so you just keep that one, and you drop the rest. So that's that, right? So obviously n cubed is way slower than n squared, right? N to the fourth would be way slower than n cubed, right? And so forth, right? The higher the degree gets, the slower it gets, right? Yeah.
Another question. A while ago, someone was in a for loop, right? And
What happened?
someone was in a for loop, and they actually did the I guess the second part of the for loop, so like I is less than the array. Outside of that for loop, but they do it in the variable instead of a faster way of doing it.
I would have to look at the code, but I'm not totally sure what you.
That's slightly less.
Not sure. All right, so let's do a bit of practice, right? So I made this thing for you guys. So can you guys go on this GitHub? It's github.com/MMOSAYED/big-O practice. I'm not being able to access your Slack, so. Huh? Yeah, it is. Yeah.
It said maybe copy paste it on Practical.
Yeah, smart. So once you get there, let's work on part one, okay? So let's do all the problems in part one. I guess let's reconvene in like, how long do you think it will take you guys? I think there's like 10 functions.
I'm just saying what they're,
Huh?
what their big old notation.
24 minutes. Let's see how you guys feel, right? Just do it, and we'll be after you guys feel like it.
We're only trying to figure out the issue.
Yes.
They work in groups or?
Yeah, sure, working group.
Is it just supposed to record the big O of each?
Just part one. Don't go to part two yet. Your DSA is not going to close book. Yeah. Never.
No, no, the three, where they have now 4 left upper grade. Is that correct? No, or no?
Oh, you guys haven't seen the syntax?
Upper's right, it's a regular one. It's not.
Try that.
Wait, what, to let VFR, right?
It's not.
I just skipped it. Me and Chloe was like, what?
It's exactly, yeah, so. Sure.
Yeah.
Ask him.
How do your capstone go? Capstone. Yep.
Wow. You guys present this. Yeah. One certain.
I think ours is 19.
Same place.
Yeah. I think so. I was kind of disappointed. I was kind of disappointed. I was
Yeah.
at moment. Because in the past years, it was like in like Google and stuff.
And they're all sort of appropriate, I guess.
The auditorium. The auditorium. They did the graduation last year. Hopefully. Yeah, I
They said
think
that when we graduate. They said that the requirements. It's not gonna be graduation.
it's not.
That's what I heard.
I don't know. Yeah, I don't know. They don't tell me anything.
Show up, slowly show up.
I haven't been here in like the weekdays. I haven't been in the booth.
It was only the third number. It was only because.
Oh yeah. On the weekdays, 'cause weekdays weekdays I would teach from like 7 to 10. And that's when you like break class and stuff. So like chill.
Even though we were still
Where's Davey? Davey. You got a job?
I think we.
Cause I got some email or something.
You can walk in with us.
What company?
You don't people know sometimes.
I see. That's why he's not here.
Oh, this is Javon from Iowa. He brings it up.
You what? Oh, okay. Yeah, that's what I heard. I heard Davey's supposed to bring the gum. That's probably what I did.
That's it. Oh, that's Javon.
Congratulations. Yeah, for one. Yeah, for one.
Oh, yeah, I didn't realize they were on. Oh, yeah, I guess it's like.
So what, did you guys cover everything for DSA? Like, did Corey go over, Corey read over anything?
To this DSA, no, that's what this week is supposed to be about.
No, like previously, like throughout the year. Like,
Yeah, we can go on, but
you guys have like nucleus.
I need a lot of those links.
Yeah, I'm not really supposed to cover like this today, but I think Dave is gonna cover it tomorrow morning. But I'll start it out. I'll start it out. Because I got math time. 4 hours is too much for big note. Especially once you guys get like flow. It's pretty simple, right?
Yeah, the day it's
Yeah, you just follow the same pattern as this. Just apply.
I'm also thinking for research again. The go for research.
For recursion?
Yeah, that's something special about it, right?
Oh yeah, I'll cover that a little bit.
It's what you do, guys. Oh, man, oh, man.
Alright, that's nice, that's what I'm gonna do. You guys done?
Yeah.
Huh? Alright. Alright, so that's like that simple O of n, right? Yeah, O of n, right? Second one, what is it? O of n. So what's the difference between this one and that one?
The reader thing is something about it isn't clear. Just, it's the same thing, but
It's just essentially what I'm saying here is, okay, here I'm giving you a direct number. I want you to iterate till this number, right? And here I'm giving you a data set, right? And we don't know the size of the data set. It could grow and shrink, but still O of n, right? So two similar things, but important distinction, right? What about this? O of 1? Why do you think it's O of 1? Have you guys seen that syntax before?
But I did try it. I just ran it.
And it works? Yeah, right? So, what happened?
It's O of n.
Yeah, it is O of n.
It's basically a little like the same thing.
Yeah, so just to like give you guys a little JavaScript lesson, right? So let I equals 0. So this syntax, right? This for loop syntax is basically the same for loop syntax that is in like every other language, right? Like C++, Java, everything, right? So it's a pretty standard syntax, and it's everywhere, right? Any like JavaScript, the syntax for JavaScript is also based off of the language C, right? So that's why like it has similarities to it. That's the same as you doing like array dot for each, right?
The dot notation. Iterative function.
Mm-hmm. Yes, right. So you could do for each. You could do for let I in array, and you could also do for let I e of array. So these are all basically the same thing in JavaScript, all right? So JavaScript has like multiple ways of doing it, and these are more modern, right? They took this from like languages like Python and stuff. So what I in array does is I basically is now the index, right? So it's gonna loop through the entire array, right? You don't have to the difference between this syntax and this syntax, right, is that this one is just going to iterate through the entire array, right? You don't have to worry about the length. You don't have to worry about anything. Just going to go through everything, right? But when you use in, what's going to happen is the variable that you define before in. So you could say I'm saying I here. I could call it whatever I want, right? I could call it mo, right? Whatever that variable is, right? It basically takes up the index at that position as it goes on. So it's gonna, like, if I console log I, it's basically gonna give me the index. Does that make sense? As it's going throughout the array. So I could say console log I, and then I could say like ARRI to get the actual value, right? Yeah?
What about the 5 plus this step? You don't have step this.
Yeah, there's no step, exactly. It doesn't, like, it's a simpler loop, right? So so this does exactly the same as this, but when you do this, you basically don't worry about the step, you don't worry about the condition or anything. It's literally going to start from the beginning, go to the end. That's it.
So this one, you only able to count one element from the array. You can't say go by two.
No. And I mean, the reason they came up with this is it's for shorthand, right? And a lot of times when you're writing algorithms and stuff, you actually iterate through everything. You don't really step for any of that, right? So it's a very common thing just to iterate through an array, right? So that's why they have that. And then let E of array, so the only difference is in and of, right? Of basically takes the actual element. So E is the actual value. Pretty useful, right? So now, whatever the value, whatever is in the array, E is always going to be the value. It's not the index, it's the value. So of and in, right? Honestly, of is way more useful. Okay? No one really ever uses in. But that's basically that, all right?
So you can combine that, like when you have for each, and you combine the for each, you have the elements and the index all in one. Is there a line where you could say?
Oh no, yeah. Here it's separate. Yeah. So yes, you're right. So for each, it's a callback, right? So in for each, you basically have the element, the index, and the array. You get back all of that, right? Cool. So because of that, right, it's just a very simple for loop, and you're just going to iterate through everything. So that's why it's O of n. What about this, func 4? O of 1, right? Because no matter what, right? If I inserted, let's say the array that I insert has a million different items, right? Right? There's a million different items. What's going to happen? It's only going to console log the first 5, right? No matter what the size is, it's always going to do the first 5, and it's going to stop, right? It's never changing based on the input that you pass it. So because of that, it's over. Okay? Func 5. O of 1, right? So something interesting, right? And this is what throws off a lot of beginners, right? Is that when you're thinking about this, you're like, okay, this is O of 1, but what if this for loop takes some time, right? Because I'm going through it like how many times? 100,000 times, right? Here's the rule, right? Like constant time could take up a lot of time. Okay? it can take up time, but what the reason it's constant time is because it never changes. No matter what, it's always gonna, even if it's taking up time, it's always gonna take up the same amount of time. It's never gonna change based off the input. Does that make sense? All right. Function 6. O of n, right? So yeah, so you have O of 1 here, O of 1 here, O of n, 2 O of n, 3 O of n, right? But to simplify it, it's just O of n, right? Function 7, n squared. Function 8, m cubed. Function 9, n squared, right? This is the one with the highest degree, so that's the one that matters. These don't really matter, right? Function 10, n squared, right? Cool. All right, pretty easy, right? Yeah, like after you learn that pattern, right? It's like you can literally apply it to any code and it'll just work. Okay? All right.
Can I see the one with the bunch again with the gap on the graph?
Oh, this one?
Awesome.
Pursuit's internet is always so slow. Where is it playing from? Outside?
I can't tell where it's going. It's outside, but I can't tell if it's like a car or like they have for a concert call now. It does sound familiar. Oh, it is all of me. Oh,
Yeah.
shit.
It was bothering me the whole time.
Oh my god. I'm so glad my girlfriend's not here.
All right. So now, let's say we have so given this, right? Given that target, given 1 and 2. Tell me again, how do you find this? How do you find the targets, and what are the time complexities of that? Why would you need 2 for loops?
First iteration is first target. One starter.
Well, okay. I think what's confusing you is because we have both the targets there, right? But let's say you had to find one target. What would you do?
One for loop and find the indexes of that target.
You just do linear search, right? So you do something like function includes the array and target 1, target 2. So you would basically do like right? That would get you the index of the first target, right? And then to find it for the second target, you just do what? You just call it again, right? And I just change up the variables. So what's the big O of this big function includes? O of n, right? Because the first one is O of n, the second one is O of n. So what does it end up becoming? Like what is the if I ran this right now, right? Target one is what? 1, right? So what's the actual time complexity if I run this? It's actually over 1 when I run it, right? In this particular case, right? And what about for target 2? O of n, right? So we know that this function is linear time, right? Big O of n, right? Even though for one case it might be pretty good, right? But it's still for the average case and the worst case, it's always going to be O of n, right? So interestingly, right? What do you notice about this array? It's sorted, right? So knowing that it's sorted, can we do something to make our searching way faster? Yeah, you could skip ahead or do stuff, right?
But it's not looking into the time, so I might.
Oh, so you're saying like based on like the target value, you would do like a conditional, and if you would check if the target value is closer to the beginning or closer to the end, right? And if it's closer to the beginning or closer to the end, you would what? You would start at the beginning or the end, right? And then do your regular linear search, right? That can work, but it's still O of n, right? It's still a pretty slow searching function, all right? There's actually a way to make this way faster. Okay, yeah. Well, how would you do it in an object? Because you're saying you want to make those keys. Okay, but how do you get an array into an object? You still have to loop through the array, right? And then place it in the object, right? Still O of n. Still O of n. So let's do that, right? So function includes 2, right? So what would you do? You would basically say for let I equals to 0, I less than array dot length I plus plus. What you're basically doing is you're looping through, right? And you're saying, okay, so const obj is an empty object, right? And then you're doing obj the array dot what? No, array of what? Equals I, equals whatever. Oh yes, yeah, true, right? And then once you have that, you can just say return obj target, right? And that should give you the answer. Yeah, but what did I just teach you guys, right? Let's say this takes O of 1 time. What is this? This is O of n. And this is O of 1. So it ends up being O of n, right? Even though this is really fast, but to get there is slow, right? So this whole function ends up being O of n, right? So that's not really useful. What else can we do you think?
Are you asking us the fastest way to search for this target?
Yeah.
I mean, we're trying to find both targets.
Well, let's focus on one at a time. Because one, if you could find one, you could find as many as you want, right?
Five, the array, over to, guess the values and searching for them.
That's linear search, though, right? Yeah. You had something?
It's kind of same thing. You have like a pivot.
Oh, pivot. Okay. Yeah.
Yes.
Oh, pivot. Okay. Yeah. So what you would do is you basically find the middle of the array, right? And once you have the middle of the array, right? So what's the middle right now? 7, right? So once you find the middle of the array, you basically compare the target with the middle, right? So in this case, the target is 1, right? What do I say now? Now I say, okay, is the middle of the array, whatever item is in the middle, is it equal to the target? If it's equal, I found it right then and there, right? I just then return that item, right? Okay, let's assume we're not returning the index. Let's assume we're just saying if it's there or not, okay? But if it's not there, right? If the target is not equal to the middle item, what do you do then?
Check if it's greater or less.
Yeah, you check if it's greater or less, right? And in this case, 1 is less than 7, right? So that means that because my array is sorted, right, it has to be to the left of 7, right? Does that make sense? Because it's to the left of 7, we can completely disregard everything to the right of 7, right? So by doing that one step, we literally cut our array in half, okay? So now that we cut it in half, we repeat this again, okay? Now we go back to the middle of the left array, and we do the same thing, okay? What does that feel like? What kind of, it's binary search, okay? That's the term, right? That's what this search is. But what does this feel like? Like cutting the array in half, checking if it's going to go left or right, right? Then going to the left or right array, doing that same step again and repeating until you're left with one unit. Yeah, recursion, right? So this is binary search is actually a recursive function, but you can also write it as a iterative function, because anything you can write recursively, you can write iteratively, right? I think I already have it written somewhere. Let me check. Yeah, so this is the recursive, right? So you're basically dividing the array in half, getting the middle, getting the left array, getting the right array, right? And then you check for the value in the middle of the array. If the value is smaller, right? then you do binary search on the left side, okay? And if it's bigger, then you do binary search on the right side, basically, right? So take a look at this later, but yeah, like I kind of go with step by step, right? Going through exactly how to do binary search, right? But essentially, you're cutting the array in half every single time, right? So that's way faster, right? Is it way faster? Isn't it way faster than the other way, technically? On the long run, let's say you had 1 million items, right? If you cut the array in half, you cut off literally 500,000 items, right? And then you're working with another 500,000. Then the second step, so that was the first step, right? Second step, you cut the 500,000 down to 250,000, right? And so forth, right? So that, can someone tell me what the, what do you think the time complexity of that is? For this binary search function. I heard all three. I heard O of 1, O of n, and O of log n. Which one is it?
It can be n because n is the exact length of the entire array and it's not as
Yeah, so okay, good point. So it can't be O of n because you're never gonna iterate through the entire array, ever. You're always cutting it in half for every step you take, okay? Every step that you take is very important that you guys understand that. Every single step. So as the program is going through its steps, right? Every step you take, you cut off the array in half, all right? And the half gets smaller and smaller and smaller, right? So it's definitely not O of n, all right? So what is it? It's log n, okay? It is log n, all right? And the way log n looks in comparison to the others, right? So this is O of 1. This is O of n. And log n is basically, okay? It's like a very slowly climbing line. It's going to gradually increase, okay? So yeah. Does anyone know like what this kind of function is called? Like this binary search logic? So this is a binary search algorithm, right? There's a very special term in computer science for this. Does anyone think they know?
Question before that, on that line graph, does that mean that?
Which one?
log n-
Oh, this one?
Yeah.
Yeah.
Does that mean O of log n is faster than O of?
At a point, yes. At a certain point. Actually, let's confirm that. See, like every time they draw these graphs, right? No, okay, all right, yeah, no. So in the beginning it starts off a little slow, as you can see, right? Like it starts off a little slow, right? But then it starts to like even out, right? So whenever they draw a constant, they always draw it kind of like in the middle of the graph, right? But that really depends on constant. Right? The constant can move up or down based on how long it takes, right? So yeah, but that's what it is. Yeah, sorry, my drawing is not as accurate. Okay. So going back to it, right? This binary search thing. What are you doing essentially? Like, what am I keep repeating to you guys? Like, what are you doing, this binary search? You're having it, right? Every step you take, you're cutting it in half, right? So I want you guys to keep this in mind, right? This is pretty much a law, okay? It's pretty much a law. Whenever you write a function that takes in the input and it constantly halves it, like it cuts the input in half over and over and over, it's a log function. It's a log function. Yeah. So that's how you know it's big O of log n. If your function is constantly cutting the size in half every step that it takes. Okay? And binary search is like the most simplest example of that, right? Yeah.
So does it answer your question? That's the name of the question is small computer science.
No. There's another term I'm looking for. It's basically what this is also called is it's a divide and conquer algorithm.
Oh, that's exclusive.
Yeah. Yeah. So it's a divide and conquer algorithm, right? So, and it's a very common term, and you do this a lot, right? And usually when you're doing a divide and conquer, it's using recursion, right? So using recursion, you would like, you guys did like merge sort, right? So, you know, like when you do merge sort, you're basically, that's a perfect example of divide and conquer. You're literally dividing up the array into smaller pieces, and you're trying to conquer this problem in smaller pieces. That's what it means by divide and conquer. When you have such a large task, right? You want to break it down into sub and smaller tasks, and try to solve it in that smaller scope. If you could solve that same problem in that smaller scope, you will find the problem in the larger scope. But that's what divide and conquering means. So whenever you have divide and conquer, or you're either halving it, right, cutting it in half, always know it's log of n. Okay, so that's how you determine if it's log of n or not. Yeah.
Are all binary search algorithms also called divide and conquer algorithms?
Yeah. Yes. Yeah, so take a look at this later on, right? But I basically have the, this is the recursive way of doing it, of doing binary search. And also I have the iterative way of doing it. So using like a while loop, right? So it's two different ways of doing it. Yeah. But essentially it's the same idea, okay? Yeah, it's I don't know if like so I wrote the DSA curriculum. They were supposed to fork it. I don't know if they forked it. Okay, there's forks. Wait, who's this? Who's that? Oh, that's her. Oh. Wow, like not even my students forked it. Yeah, so it's actually on Pursuit. So if you go to join Pursuit/DSA curriculum, they actually forked it. Cool. Anyone have questions on how do you determine log n? Yeah.
When you're doing a binary search, you're using the search that you want.
What do you mean?
Like every time you have the array,
You need to what?
you need to
You may get a copy. Yes. You may get a copy. All right, guys. Now that you know that, I think you can work on part 2. Yeah.
Array methods. What is their
O of n? Oh, I mean, what is their big O? So array methods, they're all O of n, except for like reduce and stuff. Actually, I think even reduce is O of n. Yeah, they're all O of n because all of them iterate through the entire thing. All right, guys. So work on part 2. All right. This may take you a little bit more time because there's a lot. Just what I want you to do is like literally like break it down, right? So try to break down each little part and try to solve it. And this time, you have to state the best and worst case. Okay. So what's the best case and what's the worst case? All right. Cool.
All in favor?
No, that's big. All big O. All big O. Yeah, so you can work in groups, do whatever you guys do. No. You guys didn't eat lunch? Yeah, we had lunch. Oh, cause like, my class, usually after lunch, they're like dead. You guys, you guys are pretty late.
Yeah, at night too.
Huh?
At night.
No, like on the weekends.
Oh.
Yeah, like after, like 2 p.m. it's like the worst.
That's probably I think we got used to it.
I see it.
First, they are all nice. They are very strong. And then
Yeah, we had lunch right before we started. Yeah, you guys had it right before.
Does if have on government, like the punishment?
It's constant.
So I guess this one it's long and I don't I have a question. So look at
We're actually free. Look at that.
He said I have
All I was doing was eating.
I know you ate it. Where is it? You know it? It's large. I won't finish it. Peanut butter, that's.
Thank you. I always.
I think say. You don't want a full.
They have. They have the roads. I like that. Sure. Or the one you had roast.
So during the essay, like you said that they want you to do, like, so would they want you to do a full question for each one?
Wait, sorry.
Like, would they want you to do an actual puzzle, or is it actual that version of it?
You're like a interview? You can use for each.
Okay.
What is their preference, like,
Depends on the interviewer. If they're more old school, then they will say can't use array methods. I mean, if they say build for each, then you can't use for each, right? Yeah.
I thought you were serious though, when you wrote binary search, those are reserved keywords. Binary search and mixed search.
Oh, when you're in REPL?
No, well, here, if you look at function 4.
Oh,
where it says-
yeah. You're assuming that we define the binary search function somewhere.
Okay.
Yeah.
So you're are we actually building these functions out, or are we defining multiple?
There's no multiple choice. There's no multiple choice. That's so it's easy to grade it. Yeah.
how many questions?
14, 13. I mean, if you guys ever want to like what do you mean?
That's getting back to
Oh yeah, network. No, I actually mean like studying. I mean like try whiteboarding problems and stuff. Yeah, yeah, you and then you.
I have a question about five.
I mean, we're gonna go over it. We're gonna go over it. Don't give if you know something, don't say it out.
No, it's more of like a question. We're assuming that the utility function is being declared on top.
Well, in JavaScript, technically, it doesn't matter, right? Yeah. Let's say it's modern syntax. It doesn't really matter. Right? If we're not using strict like JavaScript, then it doesn't really matter. But yes, sure. Yeah.
Just to expand what you said earlier about CS majors, only have DSA over it. But it was 4 years of that, and we're really like.
No. So, so I went. I don't like talking about myself, but like I went to NYU, right? And like the only thing so when I went into NYU and then I was a freshman, right? I was actually shocked at like the seniors, right? The seniors at NYU and like what they can actually do, because I actually started coding like before college, right? Like around like high schoolish, middle schoolish, right? And that was literally one of the major reasons I even got into the school, right? But when I got in, right, like it's like I was actually shocked that seniors couldn't do a lot of trivial things that you guys could do. So it's not really, it's not as hyped as you think it is. But yes, the only class that I'm really grateful for is the data structures and algorithms course, which is literally 1 semester, right? So it's only 1 semester's worth, right? But you guys can learn that stuff on your own, so and you should, right? Like there's a lot of like DSA videos on YouTube and stuff. Just look through that, okay? What you guys should do is using the DSA curriculum, right? If you guys know all this, you guys will be ready for like most companies, right? Well, actually, if you know like trees and graphs, right? If you know trees and graphs, you're practically Google Calendar. Like you could practically do Google and like Amazon and stuff, which is like the top of the crop, right? So if you know like trees and graphs, right? But if you know everything else, if you literally know everything else, right? If you know like stacks and queues and hash tables, linked lists, right? If you know like trees, like if you know how to like iterate through trees and stuff, you could even work at like Oracle or like other companies, right? Yeah, like it's not that hard. It's not that hard.
So you took a year to learn all that, a semester?
Well, a semester is half a year, so it's like 4 months. 4 months.
If I could interject for a second, it's like not, depending on the school you go to or what curriculum you're in, depends on how much and how often you learn something. But in my limited CS college experience and from other people I've talked to, whether it's mentors or people in the industry, like college kind of for CS kind of seems, for lack of a better word, pointless.
Yeah.
They teach a very basic understanding and basic knowledge of things. What's crucial that they do instead of learning like frameworks per se is more about basic fundamental knowledge. And they kind of do that. In my opinion, what's important in the job market is not necessarily like having that degree, that piece of paper that says, oh, I know this stuff. It's like really about what you were saying about it's competitive. And you have to be competitive to survive, and not just competitive with other people, like competitive with yourself. Like, how are you going to push yourself over the next day to do like better than what you were doing before? How are you going to increase your knowledge to appear more valuable to a company?
Yeah. So like, yeah, like CUNYs, not to shit on them, but CUNYs are very, like they don't prepare you at all. I have a couple students that are like seniors in CUNY right now, and they're CS majors, and they don't know shit. But yeah, it's honestly like you putting in the effort and the work, and like the internet has access to everything, right? So try to learn, right? There's so many, when I tell you, like there's so many YouTube videos and stuff on all these data structures. You just gotta take it step at a time. Make sure you've mastered linked list. Linked list is probably the most important data structure there, right? Make sure you master linked list and then move on to the next one. Because if you don't know linked list, you can't do the other one, right? So yeah, and to give you like an inspirational story, right? So like other than this, I also have a startup, right? And one of my childhood friends, he was actually a mechanical engineering major at NYU too, right? But then he ended up dropping out, and then he's like, hey, like I want to change my track and I want to do like CS and stuff, right? So I took him in under my wing. This guy had no like prior like CS experience, right? And so he basically worked under me in my startup for like a year, and then like I had him build a lot of stuff. And then after that, like he went out and like really like tried to like learn like the data structures, right? And he ended up getting his first job at FanDuel, right? Started off with like 95,000, right? Which isn't bad, right? But no. Nah, but like it's they actually like so this is another lesson to learn from this, right? Afterwards he checked like FanDuel's like the same position he's in, like what the actual rate is, and it's actually like 110. Yeah, they lowballed him basically. Well, he lowballed himself because he said it. He said, "Oh, I'll be fine with between 90 to 100," and the guy's like, "Oh yeah, okay, cool, right? I will give you 95, right?" And but after that, right, he worked there for like 11 months. But while he was working there, he was like after work, he was like hustling his ass off. Like he was not happy with that position, and he wasn't happy with it, right? So he started, so what you guys should really be on is LeetCode.com, all right? This is the secret sauce, all right? Like, I don't, like trust me, it's LeetCode. LeetCode is where it's at, right? If you sign in, so LeetCode has a lot of problems, right? So these easy problems are not actually easy, right? These easy problems are actually not easy. They're pretty tough. But let's say you could do like 100 of these easy problems, right? You'll be in really good shape, okay? And if you could do like 50 of the medium problems, that's kind of pushing it even, right? 50, but 50 of the medium problems, you're ready for like Facebook and Google and shit, right? So it's literally about the grind. It's literally about you putting in the work and the effort, right? And so that's what he did, right? So while he was working at FanDuel, he worked on this, right? And kept practicing and practicing. He got, and he started applying for like better companies and stuff. He went on to the on-site for Amazon, right? He got rejected from Amazon. He went to the on-site for WeWork and Oracle. He got both offers, right? And they ended up giving him like, I think now it's like 145,000, right? So it's definitely possible, right? You just gotta put in the work. And everything's out there, right? Like literally all the resources are out there for you. Like it doesn't get any easier than this, right? But it's just you having the attention span to sit down and do it. All right? Yeah.
So only they have this like if you're a paid subscriber or whatever,
Yeah.
you can like have specific questions for some specific companies.
Mm-hmm.
Would you recommend that? Like, let's say if you have it, if you pick up at Uber, they have a section where, would you recommend that?
Yeah, but here's the thing, you're not gonna be asked the same question. So these, like, for example, if any of the Google questions make it up, so these are all previous Google questions and stuff, right? If they ever make it online, they don't ask it anymore, right? But the other companies might ask them. You get what I'm saying, right? But what I'm trying to get at is, if you can solve those things, right, you are pretty much ready for a Google interview. Because it's, like, what you'll notice is that after a certain point, all these problems have a pattern. And if you could pick up those patterns, you're like, okay, like, oh, I just gotta iterate through this tree or do like reverse a linked list or something like that. And it's just mix and matching things, right? Yeah.
That iterative tree thing, is that like a binary search, is a tree just an array? I know this, is that all it is?
Binary search tree, yeah. Binary search tree is basically, yeah, it's log n, yes. So it's divide and conquer. Alright, so yeah, that's just some side inspirational. So you guys like really like kick it into gear. Did you guys finish the problems? All right. Let's take a 5-minute break because I kind of need it, and then we'll come back. All right.
It's real good.
Yes, she was at a meeting. Oh, so cute.
Why do you guys care?
I was sitting over there.
What?
I'm actually really honest, I could speak things.
Put over.
Just looking at previous conversation, right?
You went to lunch.
And also,
Were you guys here?
we had
like, you have, you start with.
That's still a big part.
Over here. Those, over here, part.
You guys have seen that?
Renewable use.
So that's basically like designer and work.
I have one of those.
Or designer. All they would do is like this all out there. And no job of that. You drag it around the shirt. It's set price, set what kind of, and all that stuff. And then, you just press on the designer going all one shop. And there's no upfront cost of money, it's sell that shirt and you make money. Sure. Yeah. What time is it? Yeah, that's when like, it's kind of slow. Yeah. It's like gifted. Yeah, it's like, you're similar, it's very hard to choose who you're targeting. Maybe it's naturally, maybe it's naturally less.
Yeah.
Yeah. It's cool now, man.
I know, so I don't know if there's anything I can do now.
But I went to Montreal.
We stayed in the same around.
Is that the main strip or what's the main strip? That's the same song. It's cool. No, it wasn't like, I was told that, that we should. At least that's good. Yeah,
I wanna say. It's.
it's a cleanup, like citywide, or you mean?
Yeah, it's good.
Yeah, it's a cleanup.
Yeah, it's good.
I mean, weekends, weekends is trash.
Trash your week long.
They do still casting back when you want to buy stuff, and that's one sign.
But more tourism places.
Serena.
If you're staying like,
Serena.
we'll all like the main streets. I mean, going into the actual conference is how much of it? Aren't you?
Yeah, this week.
This week,
Going out next week.
What's going?
I'm gonna go to my sister.
Where in Montreal?
I mean.
Is it still cold up there?
No, it's nice.
I guess.
I don't even need it. I like my way.
Where did it go? That's good stuff.
All right, let's get started, all right? Cool, so if we break this down, right? What do? What is this? What's the big O of this? This is O of 1. This is O of N, right? So what's the best and worst? Huh? The best is O of 1, right? And the worst is O of n, right? Why? Okay.
Three could be either the first or the last.
Well,
You have to look through it for sure. Check.
well, what is n in this case? Is it an array or is it just a number?
Yeah.
It's just a number actually, right? So
And if it's equal to 3, that's this.
yeah, if n is equal to 3, it's gonna stop right there. It's gonna return n and that's it. It's not gonna move on to the for loop, right? So that's why that's the best case scenario, but the worst case is that it's gonna go through everything, all right? Cool. What the hell? I put the same problem twice.
Yeah.
It was a trick question. All right. Function 3. What about here? What's the best and worst? Okay, yeah, the best is O of 1. And the worst is O of n squared, right? Cool. What do you think is the average case here, though? What would be the average case for this function? Why? Why would the average case be O of n? Like, what's the difference between, what am I talking about? Like, best case, worst case, average case, right?
Average case would be most likely, or,
The one that's more consistent.
yeah.
Right. Why is O of n the more consistent case?
Because it doesn't really have any conditions attached to it.
It has no conditions attached to it. The n squared is the worst case, but that's only if this condition is met, right? So only if that condition is met, that happens, right? Other than that, for the most part, it's going to be this, right? So that is why the average case is O of n. Cool? All right.
Can you repeat the last part?
Yeah, sure. So if you're looking at this, right? The worst case obviously has to be the n squared, right? Because there is a conditional that says if this meets it, apply this worst case, right? Right? But that's only the worst case if that conditional is met, right? If like whatever is in O of 0 and if the index of 0 and the index of 1, if you add those together, right, and it makes this number, right, then it's going to be the worst case scenario, right? So that is why that's the worst case. But for majority of the cases, for the average case, right, it's probably not going to meet these cases, right? It's probably not going to meet these cases. So it's going to end up with this. So that is why on the average case, it's O of n. Right? Cool. What about this one? What is this? What's the best case and worst case? Let's break this down. Let's break it down, right? So I know that this is O of log n, right? And this is O of n, right? So what are these conditionals checking for? Odd or even, right? So if it's odd, do binary search. If it's even, do linear search. Right? So what do you think is the Best and worst case.
Best case is the O log n.
Best case is O log n.
On the graph, it was showed that it was more efficient than the linear.
So it starts off inefficient, but on the long run, it's actually way faster than O of n.
So it is faster, or it isn't.
It is faster. But it starts off slower. It actually starts off a little slower. Okay? But on the long run, it's way faster. So if you guys were to rank it, right? If you guys were to rank the big O's, the fastest is O of 1. Next is O of log n. Then it's O of n. Okay. Then it's something else. And then it's O of n squared. Right? And then it's O of this, God forbid. Factorial. And before that, it's O of n to the x. So you guys almost never have to think or worry about these final cases. That's why I don't really talk about it, right? But just know it's there, right? Yeah. So if you do the, you guys know the Fibonacci, right? So if you do the Fibonacci, right, recursively, what is the O of n? I mean, what is the big O?
It's not very good.
The Fibonacci recursive function is probably the most inefficient function in the world, right? It's factorial. Yeah, it's this. Like, and you guys could test it yourself. I forgot what it is, but what the index is, right? But if you pass in like, I think 20 or even 14 or something, like if you pass in a certain index and you try to run it, like it will probably crash REPL. That's how slow it is. All right, so it's a very slow and inefficient function, right? So that's like the best example of n factorial, all right? But for the most part, just remember these guys, all right? Because these guys are the most important, okay? So what's the best and worst? What is O log n? Yeah, but what is it? The best or the worst?
The best.
And the worst is, yeah. Right? Everyone gets it so far? Cool. All right, now it's a fun one. All right, this one is a little large. It's a little long. So we have func5, right? And func5 is doing something, and then func5 is calling a utility function that passes in parameters with other func5s in it, right? So this is the utility function, and this is func5, right? So how do you think we should approach this? What should we do first? The utility function, right? It looks more straightforward, right? So the utility function essentially has what? O of what? O of n, right? This while loop is a linear function, right? And then that's basically it, right? These are basically constant time. This is basically constant time, or it could be linear time, depending on how JavaScript coded it. But ultimately, this entire function ends up becoming O of n, right? What about this function 5? Hmm? The whole thing, the whole thing. So the if, yeah, the if part, yes, is O of 1. But what about this log n?
It's kind of like, it's kind of like.
Binary search is a log n. Oh yeah, it is. Oh yeah, sorry. Yes, binary search is log n, right? So exactly, right? This, what it's doing here, right? Calling a recursive function that takes the left half and right half, right? What did I say? That's divide and conquer, right? So this is a divide and conquer that it's doing, right? And we know that if it's divide and conquer, it's log n, right? So, but that's not it, right? So we know that it's doing the divide and conquer, right? Recursively, but on the outside, right? So this utility function thingy, right? Is actually O of n, right? So what ends up happening is you get O of n times log n, which ends up giving you O of n log n, all right? Huh? Sorry.
Can you go through that?
Oh yeah, yeah. So we first go through the utility function because it has no recursion. It has none of that, right? So it's more easier to look at, right? More straightforward. And we can see that in this utility function, if I look at the while loop, right, it's going to be O of n, right? So ultimately, this entire function is just O of n, right? We know that's O of n. Now going back to func 5, we're going through this. We know this is O of 1. We know this is O of 1. And then we get here, right? Here, we're doing a recursive call to the left and right halves, right? Because we're doing a recursive call to the left and right halves, that's basically like a binary search, right? It's divide and conquer, right? And because you're doing that, we automatically know that that's going to be log n, right? Anytime you're dividing up an array in half and running some sort of recursive function on it to divide up the tasks, right? Anytime it's a divide and conquer algorithm, it's always log n, right? But because we're also calling the utility function, we have to multiply that by the log n. So we get n times log n, which is n log n. Okay?
So
Yeah, you and then.
on line 91, 92, can you mention previously that any kind of a function is O of n? So wouldn't both slices be O of n?
So that, well, I said array methods, like array methods that iterate through the array, right? I'm pretty sure, yeah. Like, I'm pretty sure JavaScript in this case is doing the slice method as if it's a O of n, right? But in other languages, you could make that same slice method in constant time. Okay? So it actually depends on how the language did it, right? So in this case, I'm assuming it's O of 1, it's constant time. All right? Yeah, you had a question?
So the multiplication part of it, do we do that if we're using a callback function in general, or is it because this is a recursive function that we're multiplying O of n by O of n?
So the reason you're multiplying it is because every time you, you know when you do recursion, right? You're gonna call this function again. So inside of that, you're gonna have the utility function again. So essentially you're calling the utility function the same number of times that you're doing the log n. So that's why it's n log n. Okay. Don't think too much into it. Just like try to look at it visually. Just know that you have a big O of n here, and then you know that it's n log n here. So you're just multiplying it. Yeah.
Where is n log n that chart that we have started, O1, O n, O log n? The chart that you have.
Yeah, so that goes right here. So big O of n log n. So that's the order, and it's very important, and you guys definitely should memorize that for the exam. All right? It's very important to know that, like that progression. So that goes from fastest to slowest, basically, right? So n log n is slower than a linear function, right? But it's still way faster than n squared. Got it? So like if this was n squared, n log n would be like this. So this is n, and n log n is like this. Okay? So yeah, n squared is still way slower, right? And then factorial is like that, like it's way slower. So yeah.
For n log n, we have to have partial function, or we have another basis as well.
It doesn't always be. So the log n, as I said, right? Anything you could write recursively, you could write iteratively. All right, that's a law. Any kind of function that you write recursively, you could write it iteratively. Do you guys get what I mean by iteratively? It's like using a loop or something, right? So you could always do that, right? So whenever it's the reason it's log n, it's because it's a divide and conquer, and because it's like you're cutting everything in half. That's why it's n log n. All right. So yeah. So this n log n function that we just did is actually a very famous function, right? It's actually merge sort, right? So that's actually merge sort, right? And merge sort is so sorting functions are typically slow, okay? Sorting functions are typically slow. So you have like the easy and simple sorting functions like selection sort, bubble sort, right? So things like selection sort and bubble sort take O of n squared, okay? So they're very slow sorting algorithms, okay? Then you have the faster, more efficient sorting algorithms. You have like merge sort, quick sort, radix sort. There's just so many different sorts, okay? And these are the faster, more efficient sorting algorithms, right? And these are all O of n log n. Okay? You guys got that? So if in any interview anyone ever asks you, can you make a sorting algorithm that's O of n, right? Or yeah, like O of n even, right? and you say yeah, all right, they will like press you, right? They will press you and try to be like, all right, show me how you do it. Because if you could do it, you'll basically become like a billionaire, right? No one has ever came up with a sorting algorithm that's more efficient than n log n. So it's actually a really big deal. If you could figure that out, you will work at Google, like getting paid like $500,000 a year or something, right? But yeah, always remember that no sorting algorithms get any faster than n log n, right? They can for like best case scenarios, but never for worst case scenarios, right? Any questions? All right, so that's basically Big O. I got like an hour left, so I guess I could go into like linked lists. All right. Cool. So I will talk more conceptually, right? I'm going to talk more conceptually about this, as if this was a CS class in college, right? So the JavaScript array, right? So when I do like const arr equals to an empty array, the JavaScript array is actually not an array. Has anyone ever heard that before? The JavaScript array is not really an array. Yes, yes, yeah. So one of the first languages I learned was PHP, and PHP is very similar to JavaScript, where they call the array like that, right? And then when I went into college, like my professor started shitting on me, like, no, that's not an array, right? And it's actually not, right? The JavaScript array is actually like a Swiss Army knife, okay? It's actually like a toolbox that can do many things, okay? The JavaScript array is actually an array, a linked list, a stack, and a queue. It's all of that. That's why it's so versatile. That's why you could do all these things, right? That's why, what do I mean by it's a stack and a queue? Because you could do like things like unshift and shift, push and pop, right? From the beginning and the end, right? Because you could do that, that automatically makes it a stack or a queue, right? You don't even have, like, that's already a stack and queue, all right? The reason it's a linked list is because, as he said, it holds things of different data types, right? It could hold integers, it could hold strings, it could hold functions, right? You could put functions in there, right? And that's what linked lists are for. Linked lists are more supposed to be abstract containers of things that holds things together, right? And it's also an array because you could access a particular index like that. That's the most important thing about being an array. Like you being able to access a particular index in O of 1 time. Okay, so that's a necessity for it to be an array. Okay, so that is kind of why in boot camps, right? When they're trying to teach you guys linked lists and stuff, it doesn't really make sense. Like, why the hell would you even do that, right? But you have to understand, someone had to code. Someone had to code and make this JavaScript array, right? It just didn't pop up from thin air, right? Like someone had to actually code every single piece of the functionality of a JavaScript array, right? And what kind of language is JavaScript? Is it compiled or interpreted? Interpreted, right? What's the difference? You guys tell me? Yeah.
I'm not sure, it has something to do with, compiles, it's like read together before Java gets it, it's, the other way the browser reads it.
Yeah, so can you tell me which classes in Pursuit deal with compiled languages?
So like Android and like Java and Swift or C or whatever.
Exactly, those are all compiled languages, right? Compiled languages are lower level languages, right? So there are things like C, C++, Java, Swift, all these things are compiled languages, right? And what happens is when you write that code, okay, when you write that code, the compiler, this thing called the compiler takes your code and converts it directly into this thing called machine code, okay? It converts it into zeros and ones, right? Ultimately, my laptop only understands zeros and ones, right? A computer only understands zeros and ones. Computer does not understand all these letters and stuff, okay? So that's what a compiled language is, and that's what it does, right? It's very important that you guys understand that, especially because coming as web developers, you guys only have dealt with interpreted languages, right? If you go into the workplace, right, you will, like, for example, my friend, right, like he only worked with like JavaScript before his job at FanDuel, but right when he got to FanDuel, they forced him to work on Java, right? So it's something you have to kind of know, right? You can't like minimize your scope to just interpreted languages. You have to kind of understand that there's other things out there, right? And what ends up happening is these compiled languages make interpreted languages. What do I mean by that? What do I mean by that? What I mean by that is when I'm writing this JavaScript code, right? I wrote out this code. You see how I write? I press run, right? So what is happening is this code is just a huge piece of string, right? It's a large piece of string, this code. And what it does is it passes that string to the JavaScript interpreter, right? So there's this JavaScript interpreter, which is just like any other computer program, okay? It's just a computer program that takes in JavaScript code, understands it, and runs it. That's all it does. And that's what interpreted languages are, and that's what they do. That's why when you're writing Node, right? That's why when you're writing Node, you could do like node index.js, right? Right? That node is a computer program. Node is basically a computer program written in C++ that understands JavaScript and runs JavaScript. That's all it is. Okay? So the problem here, right, when you guys are learning data structures and linked lists and stuff, is that when you're working with interpreted languages like JavaScript, Python, Ruby, right, PHP, all interpreted languages, right, you never deal with memory. Okay, you never actually deal with RAM, memory and stuff, right? But if you're dealing with C++, Swift, Java and stuff, right, you actually have to deal with memory. Okay, you're actually directly dealing with the RAM. Okay, that's why you have to tell it what kind of variable it is. So in JavaScript, when you say var x, right? It's assuming it's anything, right? It could be any type. But in other languages, you have to tell it like int x, right? And you tell it like int x. And now this x variable can only hold integers, right? And the reason for that is because the computer has to allocate little bits of space in RAM for that variable, right? And different types hold different amounts of space, right? So it's more efficient, right? Like a string would hold way more space, would take up way more space than an integer would, right? So that's why, right? So the compiler needs to know how much space and memory it needs to allocate for each variable, right? But for when you do a job like JavaScript and stuff, you never think about that stuff, right? So knowing that, right? Going back to arrays and linked lists. An array in low-level languages, and when you talk about array, right? It's actually a fixed size of. It's actually fixed size. So in other languages, when you're defining an array, you have to tell it exactly how big the array should be, right? So you have, let's say you're defining an array, right? Let's call it an array, right? You actually have to tell it that it needs to be 3 spaces long, right? So when you do that, that array now allocates space of 3 spaces. Okay? Now this array can never grow or shrink. This array will always be 3 spaces. Yeah.
That's in a compile.
That's in a compile language, exactly, right? So that when you're talking about array in computer science terms, that's actually what you're talking about, right? But then we as developers, like front-end developer, like JavaScript developers in general, when we talk about arrays in general, we talk about the ones that expand and shrink, right? Does that make sense? So I'm just trying to teach you guys like more computer sciencey stuff, okay? So now, this array, you could plug in whatever numbers you want. Like you could put like 7 in here, 8 in here, 100, right? And you have access to these index values. Like it's the same exact thing. This is 0, this is 1, this is 2. Same exact thing. But the only difference is that this array does not grow and it doesn't shrink. Does that make sense?
Can you make a copy of it and like the data inside it and make the array bigger? Instead of 6 slots?
Exactly, so that's what you have to do. You would have to, yes, make a copy of it and then allocate a new array with a bigger size, right? Yeah, right? So that's an array, right? In every other language, okay? And the reason it's constant time, the reason you're able to access this in constant time, have you guys ever wondered why you're able to say like array 1, right? Pass in that index, and you get back what, 8, right? Why is that constant time?
Because we point to the memory that has that data.
Exactly, right? So basically, the reason that's constant time is because think about RAM, right? So imagine this is RAM, right? Think about it as like, let's say this is a let's say RAM is a room, and it's a movie theater, right? It's a movie theater, and each row is a row of seats, right? In a movie theater. And each seat is like this, right? You guys know what I'm getting at? So this is RAM, okay? Like this is actually RAM. Like when people talk about RAM, this is RAM, right? And what ends up happening is each of these spaces is a space in memory, right? So when you're defining a variable, right? It's putting that value in here, right? And then you define another variable, it's like putting it in here, right? And it basically has the address to that point in memory, right? So that is why when you do this, you're able to get it in constant time because you have direct access to that place in memory, okay? But here's what happens, right? Let's say you're like, I have like Google Chrome open, let's say I have Visual Studio Code open, right? I have two different programs open, right? But these programs share the same RAM, right? They're sharing the same RAM. My computer only has the same RAM, right? It's only one piece of RAM, like whatever, 16 gigs, right? But what ends up happening is, how do you know like Google Chrome should take up like how much RAM it should be taking up, right? It shouldn't be RAM hungry and take up like half of all my RAM, right? Google Chrome should not take up like 8 gigabytes of my RAM. That doesn't make sense. Why are you taking up 8 gigabytes of my RAM if you're only going to be using like 300 megabytes, right? So because of that, RAM is kind of like first come, first serve, right? It's like if people were coming into the movie theater from the exit, right? If you were coming to the movie theater, you're gonna fill up the spaces as you come in, right? So you could technically have some memory here that's for Google Chrome, and then some Visual Studio Code memory here, and then again Google Chrome, then Visual Studio Code. You get what I'm saying? It's not really. It's like when it's being placed, it doesn't really matter what program it's from, but it knows what program it's from, right? But when you define an array like this, right? I'm saying, hey, I need my array to be 3 spaces, right? What you're doing in RAM is you're saying, hey, I got 3 friends with me, right? I'm entering this movie theater with 3 friends. We need our seats right next to each other. We want to sit right next to each other. Does that make sense? Right? You're going into a movie theater and you're like, hey, like I want to sit with my 2 other friends. Okay? So that forces the RAM to say, okay, here, you guys get these 3 seats. This is your 3 seats. That's what you're doing actually when you're building an array. Okay? You're building you're taking up adjacent places in RAM. Right? I know that's a lot. I'm basically oversimplifying like a lot of CS concepts in like 15 minutes, so it's a lot, right? But do you get the analogy of like a movie theater and rows and seats and people coming in, first come, first serve, and then if you want to sit with your friends, right, which is an array, you sit with your friends, so you sit together. Does that make sense? Yeah.
What happens when you define in JavaScript?
What happens when you define JavaScript, right? All right, cool, yeah. So now, right, so this is, when you, back in the day, right, when languages first came out and stuff, this is the only way you could store a collection of data. This is the only way. This collection of data would never be able to grow or shrink. Okay? It would never be able to grow or shrink. Does that make sense? And that's kind of problematic, right? Because you never know how much data you need, right? So what people would have to do back then is they would say, okay, give me an array with 10 items, right? And if I need more, I'll just scrap that one and make another one that's bigger. I'll scrap that one and make another one that's bigger. Okay? Does that make sense? So that's what they used to do, right? But then that became really inefficient. Like that's like, why do you think that's inefficient? Let's say you go into a movie theater with 10 friends, right? And you all want to sit next to each other, 10 people. And you do, right? And then out of nowhere, 2 of your other friends call. Right? You guys are already sitting there, right? And 2 of your other friends call, and they're like, yo, we want to come through too, right? Now you need an array of what? 12 items, right? But you can't expand anymore, right? Because let's say you're only taking up this amount of space, right? This is how much space the RAM is giving you for your thing, right? And then like, let's say like, for your program, and then let's say for like another program, they're already using these places. That's what happens in RAM. Like, other programs are already using this space. So how can you grow? You can't, right? You can't grow. You would have to scrap this all together and say, hey, give me like a fresh row, right? That's how it happens in like C++ and Java and stuff, right? So that's really inefficient. And then what happens if like you go down the RAM, right? And there's no rows left, but you need more space. You can't have it all together, right? So that's a problem. Yeah.
Theoretically, then, if you have like the first block be like also a list of holding where everybody is in order. That way, if the 10 came in, they could get these positions next to you, and then they could be together on that block with the number, but it could give you like the index of where they actually are.
What you described right there is actually a dictionary. Right? That's a dictionary or a hash map or a hash table or what we call in JavaScript an object, right? A JavaScript object, that's what you basically described. That's how you would make it, right? So that's what I mean, right? People literally had to play around with this. Like they didn't have like languages that were like as like versatile, right, as JavaScript, right? They had to deal with these kind of constraints, right? So because of that, they came up with all these different data structures to make their jobs easier and faster and more efficient. Okay? So someone, I don't know who, right? I have no idea who it was, but someone decided, hey, why can't we do this? Instead of defining an array like this, right? Like a collection of data like that, like sequentially, they don't technically need to be next to each other, right? They technically don't need to be next to each other, but they need to know where the other dude is, right? Where the other person is. So imagine if you had like a 7, right? Put the 7 in here, right? And all of this is blocked out by some other code, right? You could technically put the other number, 8, here, right? And then just point to it. And then you could have the other number, 100, here, and then point to it. Right? 7, 800. 7, 800, right? It's in order, right? What is that? That's a linked list right there, right? So that's the foundation of a linked list and why people invented a linked list, right? So that's why you have class node. You can barely see this, right? Whatever, class node, the constructor. I'm not gonna spell out constructor, right? And then this dot value, and this dot what? Huh? Next, right? So what you end up doing with a linked list is each of these little blocks is a node, right? Each of those blocks is a node in memory, right? And you chain it together, no matter where they are, it doesn't care, it doesn't matter. You're just pointing to the next node. right? So because you're pointing to the next node, what you end up with is like this, right? You end up with right? And this last node doesn't point at anything, right? Doesn't point at anything because there's nothing left to point at, right? So that means that's the last thing in the list, okay? So that points at no. That's how you know that this list ends right there. If it points at no, that's where it stops because there's nothing else to point at, right? So does everyone know why the difference between like a conventional array and a linked list based off the graph and stuff?
I understand where the node points at null is when it stops. Is that the head or the tail?
That's the tail. So, good question, right? So, this is the head, right? This pointer thingy is called the head, right? This is not the tail actually. This is just part of that node. You see how the node has a next, right? If you're not giving the next a value, it's undefined or null, right? Right? It's undefined or null. So that is why you have like a dangling pointer, right? Which kind of looks like a tail, but it's not, right? But there's different ways you could define a linked list. One of the ways, and the way I like to define a linked list, is with a tail. So you could have a pointer that points at the last node, which is the tail. So that would be, this would be the head. The head will always point at the first node, and the tail will always point at the last node. Yeah.
So when you have a linked list, that memory setup, what if like one of the nodes has like large amount of data or something? How is that?
Yeah, so in other languages, when you're defining a node in other languages, you actually have to tell it. You have to tell it something. Like you put this placeholder called t, right? And the value has to match that. So you're basically saying this node is going to hold integers, or this node is going to hold a string, or etc. But when you're thinking about it in JavaScript, you don't have to think about it.
So when JavaScript is interpreted the array, does it act like a linked list in the actual memory?
Yes. As I said, right? Exactly. Yeah. And ultimately, it's a lot. It's just a lot. Ultimately, like the interpreted code basically gets passed to the compiled code, which then deals with it. You don't have to know all of that in depth, like I'm saying it, right? Just know that there is a difference, and this is the reason why people talk about linked lists, is because when you're defining a linked list, you're essentially creating the foundations to building all these complex abstract data structures. Okay? Because this is the foundation to every other data structure. Right? Because this is a linked list, right? So that's a linked list, right? That's a tree, right? That's a graph.
Yeah.
Right? So that's what I mean. You gotta know this. You have to know this. Because if you can't do this, you can't do that. Right? So yeah.
So just to confirm, with, when you go to the movie theater, the first person to sit down is the head. The last person to sit down and then come in later is the.
Yeah, but they're sitting in different spots.
And they sit in the spots as the tail. Now, if they have like each other's cell phone, that
They
would
have
be
what?
like a cell phone, but only one other person on their left direction, that would be like a tree. And then.
That's not how it goes.
It's more like a double linked list, if they have a cell phone with nothing.
Yeah. Then it becomes like a double linked list. Yeah. Yeah, so we're assuming that like we're taught, it's like, all right, so like, let's say, so let's say Mo, Corey, Reed, right? We're sitting at the movie theaters, right? I only know where Corey is sitting. Corey only knows where Reed is sitting. And Reed doesn't know where the next person is sitting. That means that there's no next person, right? You get what I'm saying? But Reed doesn't know where I'm sitting, right? I only know where Corey's sitting. Get it? So that's where the pointers come in. That's what it means by pointing at something. And it's like, you know, pointing is as simple as like just saying this dot next. What is the next node? What is the next node? Okay.
And the tree is a correlative adjustment.
If yeah, so a tree would be like a Corey knew where someone else was sitting. If Corey knew where two people were sitting,
And that would be a tree.
that would be a tree. Yes.
So if you know where Corey's sitting, you can see Corey can see who's like on his left or right.
Yeah.
And they can see maybe who's on the.
Yes. But that's a binary tree.
Not a graph.
Reed knows where you're
A
sitting.
graph is a reading adjustment of system.
Yeah. Yeah. So I think like graph is more abstract, but I think the best way to describe a graph and like a practical application of a graph is Google Maps, right? Let's say you're trying to go somewhere, like you're trying to commute somewhere. Google Maps has to determine what trains you should take and what stops you should get off and get you there in the fastest time, right? Like Google Maps is not going to tell you like take some crazy route around the city to get to somewhere, right? It's going to give you like the fastest route. Take this train, get off, transfer to that train, right? At this station, that's a graph, right? And who's the Uber folks here? Yeah, so that's what Uber does too, right? So those are graph problems, right? Graph problems are that. Like Uber's whole application is a graph problem. How do you take this car to this place with the cheapest price possible, right? Or if you want to be evil, with the most expensive price possible. When you get up to graphs, right? What ends up happening is you see these pointers, right? They have different weights, so they have values. So this could be like 8, it could be like 1, this could be like 2, right? So that's like the length, right?
Are all the values going to be unique?
It depends. It depends, yeah. So basically what this means is if this is New York and this is LA, right? If this is New York, this is LA. Like this is like the total distance to go from New York to LA.
Also, the 200 is like actual measurements of how far apart two things are from each other. So
Yeah. But you could like give it. You could.
like a ratio. Like
Yeah, you could create whatever metric you want. Yes. That's how they do it. That's how Google Maps and things like that calculate how do you like calculate the GPS? Like, how do you get from this place to that place in the fastest time possible? That's a Google Maps. It's literally a graph. That's also how like Facebook determines like who's friends of friends of friends and stuff. How do you do that, right? How do you find out mutual friends? That's all graph. In Facebook, everyone a relationship like adding as a friend is like that, right? It's like a pointer. And then this guy is friends with this guy, so these guys are mutual friends, right? So that's how they do it.
So is it like a big graph situation, is it like more than one thing connected to something, so it's just trying to figure out the best actions to get to where it wants to go?
Exactly. Yeah. Shit, I just realized I was supposed to cover this tomorrow. I thought. Let's still do it tomorrow.
You won't tell anybody.
We can do it again. Now I have to figure out what else I have.
So many things. I mean,
So everyone gets this, right? So I think Dave is gonna cover a linked list and stacks and queues tomorrow morning. So he'll actually, I think, do the code for this, but I'm more talking about a conception, right? I'm trying to give you guys like the CS knowledge that you guys don't usually get through this, right? All right.
Is that what LinkedIn is?
Yeah, LinkedIn is a graph too. Yeah, 100%. Any kind of social network is a graph. Right? Yeah. So you Uber guys, right? Uber guys. So I highly recommend you look into this, right? Uber guys, right? Because you guys have that Uber interview. But let's say, right? Let's say we have what is this that I'm drawing? That's it. Yeah, it's an array, right? But that's basically a graph. I mean, it's like a grid, right? It's a matrix, right? So this is actually a very common problem they ask in like top companies, okay? And like my friend that did on-site at Amazon, he actually got asked this, right? So and Uber would definitely ask something very similar to this, and they have asked something very similar to this. And it's that, let's say you're starting here, right? And you have to get to another point, right? Imagine this is like an Amazon factory, right? And the robot has to pick up a package and go to another place in the factory, right? And these are obstacles, right? The ones are obstacles. How do you get to that point with the fastest path, right? So that's a tough question, right? But it's definitely something that Uber and Google and Amazon asks, right? So look into this, right? Matrix problems. If you want to be really prepared for the Uber interview. Yeah.
Is that like base or pathfinding stuff, or is that?
Yes, this is pathfinding, yes.
don't you go through your thing with your pen?
With the what?
A pen?
My thing?
Yeah, your notes.
Oh, my notes. Oh, yeah, sure. Yeah, so very important to understand that Node is the foundation and the building block of every advanced data structure, right? So nodes usually have a constructor. Yeah. think so. I think it's still taping. Yeah. Right? And the constructor is, the node is very simple, right? It's just a constructor, and then you're assigning it the value, right? And then you also have a this dot next, and you assign it to null, right? So when you do that, right, what you can do is you could do this, right? You could define variables like node 1, node 2, node 3, give them values of 1, 2, and 3, right? But they're just separate nodes. So you see the first one is like 1, right? The first one is just like 1, and it's pointing to nothing. Then the second one is 2, and it's pointing to nothing. Third one is 3, and it's pointing to nothing, right? Not very useful, right? The time it gets useful is when you start chaining them. So if you do like node 1 dot next is equal to node 2, what are you doing? You're basically saying, hey, node 1, take this arrow and point it here, right? And if you say node 2 next is equal to node 3, you're basically taking this arrow and you're pointing it here, right? You got a linked list, right? But that's manually doing it. Yeah, that's like manually like taking a node, getting it to point to another node, right? Plugging it in. That's manual, right? So that's why you have a container class, all right? I recommend you guys look at these notes, right? I spent a lot of time writing them, okay? But yeah, anyways, so the container class is basically a head, a tail, and a length, right? So what you end up doing is, all right, you basically, let's say we wanted to define the push method, right? This is how you would do it, okay? So push method, you create a new node, right? You take the current head to come after the new node, right? So let me draw this out. So let's say you have a linked list. Oh, thank you. Yeah, yeah, much better. Yeah, when it's this good, I sometimes get scared to Sharpie. Yeah. So let's say this, right? We have a linked list that's like this. So to push a value, right? Add a value at the front of the list is known as a push operation. Okay, so when I wrote this, I wasn't trying to follow the JavaScript conventions, right? Because in JavaScript, when you push, it adds it to the end of the array, right? But in this case, it's added to the beginning. Okay? So let's change it from push to what's the JavaScript equivalent? Unship, right? So let's say we're building unship, right? This is how you will build unship, right? So you create a new node, right? So create a new node and assign it the values. Let's say you're trying to unship 5, right? You're gonna have five, right? So we create the node. Next step, assign the current head to come after the new node, right? So new node is this. New node.next is that arrow. Where's the head? This is the head, right? Of the current linked list. So what I do is I'm saying this next pointed at the current head, right? So I get rid of that arrow. And I'm basically saying that. And then I'm saying assign the new head to be the new node you created, right? So to do that, that, all I gotta do is now add the new head like that. And if there is no tail yet, let's make a new, so this is working with a tail as well, right? But that's basically it, right? That's how you push something to the beginning of the linked list. Unshift.
If there's no
Unshift list.
then the tail would even. If you was, instead of making out head, you make a tail. Instead of making, you put it in, you know, as the head, you put it in, you know, as the tail. So that is pushing,
Yes.
but this not as arching as second class.
That's if like this condition, the if statement is if there is an empty linked list, there's no head or tail, both of them are null, then that's why you need them.
The DSA exam, right, if the methods can exist within this class, we have to make the functions for the class. Like,
Yeah, you're gonna make the functions. Okay? So what is the big O for this? O1, right? This is just O1. So very important thing to understand, right? Because we have the head pointing at like the linked list class in the head that's pointing at the head, right? Because of that, we have direct access to insert things to the beginning of the list in constant time. Right? Yeah, I think it'll make more sense.
Because we don't have to go through the array.
Exactly.
Very doesn't matter at all.
Exactly, right? Because you don't have to go through the array, it doesn't really matter, right? All right, so how about, let's work on, so we just did unshift, how do we actually push them? So unshift is adding it to the beginning, pushing is adding it to the end. How do we do that?
That's what's it.
Let's assume we don't have tail.
But I think actually fine, too.
Yeah. So in this case, I'm showing it with a tail, right? But in many interview questions, they will actually tell you that you don't have a tail. It's just a singly linked list, right? What do you do then?
You define, this no tail, make your head.
The head is 5, right?
Right.
So let's say I want to insert 3 to the end of the list. How do I do that?
It's not next.
Yeah, right? So what I have to do is I have to create a while loop, right? So while, right? I have to basically create a while loop, right? I have to start at the head, create a temporary pointer, right? Call it something like current, right? The current node, right? And then as long as the current node dot next is not equal to null, keep going, right? I basically do current is equal to current dot next, right? So that's basically traversing through the linked list, right? So I start at the head and I say, hey, is the next null? Is the next null? No, right? The next is a null, so I could erase this. And now my current is that, right? Now I ask myself, is the next null?
Yeah.
Yes, right? I stop the while loop. I don't move on, right? And now I have access to the last node on the list. And because I have access to the last node on the list, I could then take this and make that the next, right?
What if you,
Yeah, I remember.
How is that not open end? It's a total.
Wait, sorry.
How is that not open?
This is O of n.
Oh, it is open.
Yes,
I
yes.
was saying that the link list and users are-
No, that's the point I'm trying to get at right now. Is that, if we had a tail, it would have been O of 1.
Because then we just wonder if it's a tail.
Exactly, because if you had a tail, right? Like if I have a tail right now,
Oh.
if I have a tail right now, I could directly access this list, right? And then plug the new value there and make that the new tail, right? But because if I don't have a tail, then it's O of n, right? Then it's O of n. And I have to iterate through the list. So just by adding a tail, you make this way more efficient. Okay? So that's why it's good to have a tail. It's good to have the head and the tail. Because then inserting inside becomes O of 1 time. Yeah.
You have just said, while there is not a current dot next, while there's no current dot next, meaning that the next one is null, then I have to.
Yes, it's the same way of writing it. Yeah.
And also line up saying, I would say just say this dot, you can't say this dot and you have to say this dot current dot next.
No, this example is if we didn't have a tail, you have to traverse through the entire linked list.
What's the last line? Doesn't to be able to get the tits out. You say,
Oh, yeah.
this is current.
Yeah, you do current dot next is equal to new node. Yeah. Any questions?
So you define a new node, which is 3. Then
You get
traverse through the.
traverse through it, you get to the end, you find the end, and then you're saying, okay, take that end. So this current dot next right now is the end, right? Then you say, okay, that next value, let me make it to the new node, right? Being able to traverse through the linked list is extremely important, right? Even for your exam. So please know how to traverse through the linked list. Okay? And it's pretty much as simple as this, right? You basically have a current pointer that starts at the head, and then you just keep moving through using a while, right? And I mean, like, all the notes are up there, right? Like, you guys could, like, I highly recommend trying to write these, like, all these different methods on your own. And if you can't get it, then look at the solutions. But it's really gonna help you out. Like, try to define all the functions. Like, if you look at this, these are, like, we have literally all the methods. Like, we have push, append, print, node at index, pop. Yeah, we have the answer for all of them. And then there's like an exercise where if you want to go further, you can fill those. Yeah.
So when you say it's important that you make a table. That just means in the constructor, when you put in this data, also put this data here.
Yeah,
That's
yeah.
enough.
No, that's not enough. You also have to, in your push logic and stuff, you also have to change the tail if the tail is changing, right? Like in this case, if I add another linked list, like if I add another node here, like 5, right? I add 5 here. This is not the tail anymore, right? 5 is the tail. So I have to shift the tail from that to this. Okay?
You know, like, we're able to, like, you know, break, break out like minus one, it's like, that would be what the hand.
So, you're talking about like the square bracket operator, right?
Yeah.
So in other languages, right, you could define the square operator for your class. So they basically define some sort of logic for the square operator, right? Square operator is basically the same as array that at index, right? It's the same exact thing, right? They just did operate, there's this concept called operator overloading, where they plug this logic into that. But in JavaScript, you can't do that. Like, they don't let you do that. But yeah, that's how that happens. Yeah.
How long do you think it will take us to learn all that?
Learn on what?
All the stuff you've been showing us and the stuff we got to do. And, you know, maybe a couple months we'll have it. Nanos depend on all this, like, you got it.
You could definitely do it. Like, you guys, you could definitely, if you spend like, you could definitely get a really good job within 2 months. All right, like I'm talking about like 90K plus. Yeah, seriously, you could definitely do that. You just got to put in the time to learn this stuff.
And then how many hours a day are you
I don't know, all of it.
All the hours?
Are you coming back tomorrow?
Yeah, I'll be back tomorrow afternoon.
And the rest of the week?
No, only tomorrow.
Oh, no. Jimmy has you every day.
Unfortunately, I'm not the day's instructor. Yeah, you can come over here, guys.
So 6.0, from what you understand, is the 3 but classes are nights. So